take it at the same time. I'm Dolph Schluter, and I'm going to be teaching this course. And the people in this room are sort of a mixture of students who are taking the course, and please sit yourself comfortably. And those who are eavesdropping, please take a seat at the back. And you're more than welcome to attend, participate if you're not registered in the course. Of course, I can only fit like 24 students in the course because of limitation of the presentation times. But anyone's welcome to participate. And when we do the workshops, we can spread out among the rooms as well, so you'll have more than necessary room to do the work. So this is an outline of what I'm going to talk about today, just an introductory lecture. Here's what the course will be like, operationally. So every Tuesday we'll meet here, and the first hour will be a presentation. The first one is next week, and followed by a discussion of papers. And I get 2 students present, 2 students moderate the discussion, and everybody gets a chance to do that once during the duration of the course. So, and then in the second hour on Tuesdays, I'll give a lecture, like I'm about to do now. And then Thursdays are our workshops. And I'm glad that many of you could be here today, Tuesday, even though it's officially orientation day, because this means we can get started on our first hour workshop this Thursday, which is just an introduction to R. So has everybody tried R at least once to have some familiarity? More and more it's happening at the undergraduate level. There's no exams for the course. There will be 3 assignments. There's no textbook, but at the website for a course there's links to a book page that talks about some of the resources that are available to you. There's a growing list of R books available, and there's a series that is available through the library, so you can actually read the book online. And I put links there for everyone that I could find. First presentation and discussions next Tuesday, and so I need 2 volunteers to present and 2 volunteers to moderate the discussion. So the first presentation will be on graphs, and I'll assign a reading, how to draw a bad graph. I'll put a link in the end of this slideshow. Okay, in the first workshop, Thursday, just an introduction to R. So lecture days are going to go like this. All of you will have read the paper. The paper is online. There's a link to it. So read it beforehand. And then 2 students will make a presentation of the paper, and I'll sort of give you an idea of what is expected. And it's not just a presentation of the paper. The paper is kind of a starting point. Read the paper and think, okay, what are the most salient features? What are the most important ideas in this paper? What do I need to get across to the rest of the class that represents the essentials? What does the issue mean for us, your graduate students in ecology and evolution? How is your work affected? What does this mean for you? And any additional opinions that you've come up with or found on some of the issues that you'll read about. And then there's a whole class discussion that takes place, moderated again by 2 other people. And the idea is that you prepare, if you're a moderator, you prepare a list of 10 or so questions that you'll use to seed the discussion. And you'll also moderate the discussion. If someone is going way off on a tangent, your job is to reel that person in and then maybe suggest another talking point to continue. Then we'll have a short break, and then I'll give my lecture. So as I said, the first workshop is Thursday. Bring your own laptops and have the latest version of R installed. If you don't have a laptop, or you don't want to bring it in, or you forget it, just let me know in time, and I'll bring an extra for you to the workshop. The Biodiversity Center here has spare Macintosh computers. And all the workshops are online. You can access them now. And the idea is to work through the problems on the website, on the workshop. And then there's also links to our tips pages that I created sort of around the topics that we cover in this course. So that will be a useful place to get help. And the idea behind the workshops is start by trying to solve the problem yourself. And if it's not working or you're stuck, ask the person to your right or ask the person to your left. And you'll sort of slowly come to realize that these people on your right and on your left are actually useful. You can maybe work through, solve some of the problems together, and then if you're stuck, you can ask me. So the workshops, 2 hours. This room is reserved for 2 hours, but of course, a day with only 2 hours of R is not enough. But the workshops are deliberately longer than 2 hours, not because I want to punish you or anything. The idea is to work at your own speed, get as much done as you possibly can. There's no, you don't get a score at the end of the workshop for how far you got through. I treat these workshops as exercises for you to practice, and there's more on the workshop than probably you need to know for this course. But in a year from now, you're going to go, oh man, I forgot how to do this particular kind of analysis. You'll be able to find this workshop, it'll still be there, and you'll be able to finish it or start from the top again. So it's intended to be a resource, not just a workshop for that 2 hours. Okay, so go back, get practice in the future as needed. I have to give you a grade for this course. So there are 3 assignments, and that'll cover half the mark for the course. And then your presentation will be 20%, moderating will be 20%, and then sort of backbench quality participation in discussion. Each of you will be, will face the task of having to motivate everyone else in the room to discuss, to start talking about some of the issues raised by the moderators. Each of you will be a moderator. You know that the person moderating in a particular week is a fellow graduate student who is suffering at the moment, who's trying to get you to pick up the thread and run with it. So I hope to maybe encourage you to do that here with this final little token of gratitude. And before the presentations and the moderating, come and talk to me and I'll give you an idea of what's expected in these things. For all of these efforts, I'll give you pointers. I'll say, for the assignment, there's a list of things that I might ask you to do as part of the assignment, like draw a graph. But if I forget to say draw a graph, ask yourself, what has he been emphasizing here in lectures? Oh, he started with graphs. In fact, next week is all about graphs. Probably that's important. I shouldn't have to ask you. So the instructions on the assignments are suggestions. They are not a complete list of what is expected of you. I'm not going to list all the expectations. I expect you to rise to the occasion. And if you have any questions, just ask. So the website for the course, redesigned, written in R Markdown, which I just learned this summer for fun. It's not that hard. It's a great tool for making reports. I do try and update it every time someone makes or sees a mistake or thinks I need to add something, or I think I need to add something. Just hit the refresh button to make sure you're seeing the most recent version. The lecture overheads will always be put there in PDF format before the lectures, so this lecture is already there. I put it there yesterday and the day before. All the readings will be there. The discussion papers, all the assignments will be there as well, so make a link to the website. I also mentioned that there's a list of recommended books that might be useful, and our tips pages. And for this week's workshop, there's a calculate page and a data page, and those 2 pages will be useful in the workshop that we'll be doing this Thursday. I said there's no books required for the course, but there's a couple. I think I say this later, but I am expecting that everyone else has taken an undergraduate level course in data analysis. So this course that I'm going to give you now is intended as a second course. If it's been a decade since you took your undergraduate data course, maybe you want to refresh your memory on some key topics, and I'm going to help with that shortly. When it comes to thinking about books, I like this one. Mike Whitlock and I have taught the Biology 300 course here for many years, and sort of this book is based on our lecture notes, and it's a pretty reasonable introduction. I'm sure you have your own textbook for the course that you took, and it's good to look at it again. As for a second stats book, maybe this is my favorite, by Kryn and Keogh, Experimental Design and Data Analysis for Biologists. I find it very informative. It's fairly dense. There's nothing about R in it, but it's all about basic principles for analysis of variance, linear models, and that sort of thing. So often if I have a question about what I'm teaching, I'll start there and see if it answers it. So here's a list of lecture topics. I say tentative, but it's pretty much set in stone. Every once in a while I think about changing the last one, but I haven't done that one yet. We're going to basically do some basic stuff on graphs and experimental design, and then we're going to do linear models, and pretty much everything that comes afterwards is sort of founded on some of the principles that we've learned in the linear models section. So that will be really where we start doing hardcore data analysis. So this course, why does it exist? So amazingly, my colleagues sent a poll around a number of years ago to the graduate students in the Biodiversity Research Center and said, if we had a new graduate course, what would be your preference if we were going to teach a new graduate course? And there were a bunch of suggestions, and then a vote was held, and this one came to the top. This is the course that graduate students said that they wanted. So it was created because graduate students said that you wanted it, and grad students taking the course, you're welcome to help me improve it as well for future graduate students. As I said, it's a second course. I'm assuming that you know what analysis of variance is. I'm assuming you know what linear regression is. And we'll take it from there. Basically that's where we'll start. As I said, if you're eavesdropping, bring your own laptops. We'll spread out for the workshops down the hall. Save the best seats for the paying guests. And I already said something about textbook. Okay, who am I? I'm not a statistician, but I have basic training. I've been analyzing data for a long time. I've made mistakes, corrected them, and you will be the beneficiary of those corrections. So I can answer most of your stats questions right away, but maybe not all of your stats questions. And some might take me time, but I'll come back with the best answer I can muster. I started using R because my students started using R. Before R, there was S, and then S+, which was a commercial. And they ran only on Unix and on MS-DOS. But R was created and runs on every platform, which is why students started using it. It's absolutely free. And R basically drove the commercial version extinct. I'm not a complete R expert. I have a head start on most of you, and I hope to hold this edge until the end of the course. But I can't guarantee that. And in this course, while you are taking this course, and afterwards, you will learn things. You'll discover things that I don't know about. You will tell me these things. I've used R on Windows and on Mac. It pretty much looks the same. A lot of people use RStudio as well, and I'm kind of getting used to it. I'm not as proficient in RStudio. And if something goes wrong in RStudio, I probably can't help you, but well, I can help you try and figure it out. And I'm going to hold office hours 3 to 5 p.m. Every Tuesday. And my office is just down the hall. So why do I think you should take this course? Well, I think it'll help you prepare for research. So a lot of methods are used in the papers that you read, and those methods have names that aren't things that you learned in your first course as an undergraduate. You learned the two-sample t-test and linear regression, but a lot of sort of analysis in modern biology uses other methods, and my aim is to introduce those methods to you in this class, or many of those methods. I also think, I'll tell you a little bit about data management later, but mostly it will be about analysis. One of my hopes for this course is that I find that first-year graduate students almost have fixed action patterns when it comes to p-values, and I want to get you to focus less on p-values and more on magnitudes, and we'll provide you with some of the tools for doing just that. And there are a lot of sort of approaches that are still being discussed by biologists and by statisticians about new innovative approaches to analyzing data. I want to introduce you to those, and also through the discussions get you to think about those and what they mean and how they can be used. I want to introduce you to this amazing statistical environment called R, which in my mind is better than just a computer program for analyzing data. In many cases, it's the analysis environment where you can carry out some new analysis that somebody has just designed. Typically, if somebody invents an entirely new method, they'll usually make an R package to go with it. And I find, especially with linear models, which is where we'll start when we analyze, start crunching numbers, I find that using the linear models tool in R helps you think about linear models and gets you used to thinking about linear models, and that helps you think about data and analysis and what it means. So it's more than just a way to crunch your numbers fast. It actually helps you think about how you analyze your data. So there's two ways I could have taught this course, and one is deep foundation in a small number of topics, and the other is a superficial coverage of a number of topics. So I've chosen the latter. So we're not going to, we're just going to have a week on linear models, and then you've got to do an assignment on it. And you might find that you might have to dig around and get a little more practice, do some reading. My idea is that I'm going to introduce you to sort of a lot of the methods that are used today, and we'll think about what they mean and how you can use them. But when it comes time to analyzing your own data for your thesis, and you need some of these methods, you're probably going to have to go further yourself. But there are people around who can help with that too. I already said, we'll start with linear models. And the purpose of the workshops is that I don't know how you learn, but I learn by doing rather than by reading. Pretty much everyone nodded when I said, have you ever tried R before? So much of this is not going to be new to you. So it's a language and an environment for statistical computing and graphics. It's free under the Free Software Foundation's general public license. It was inspired by S that precedes it. S was developed many years ago by AT&T Bell Labs, which I think might be called Lucent Technologies, by John Chambers and a bunch of others. R was created more recently as a sort of an open source version of S by Robert Gentleman and Ross Ahalka. Ahalka and Robert Gentleman. These are the two R's. And Robert Gentleman is a UBC product. He now works for 23andMe. But the current, R is kind of like a Wikipedia for geeks. It's a huge project. There are a few people that help to keep it organized, but contributors come from all over the place. And it's free. Not only can it do just about everything you'll ever need to do, it's free. So most stats packages will cost you like $1,000. Why would anyone even use them anymore? It runs on all platforms, and they're sort of the core package, and then there's all these add-ons that you can install that people have created for free and make them available to us. So here are some of the ones that I've used. We'll use EM-means and probably ggplot, but there's just an incredible diversity of packages out there. I've never created a package, but people in my lab have. It's fantastic for data management and data manipulation. It's incredibly fast at carrying out operations on large arrays of numbers. It's got fantastic graphics capabilities. You can fit models and visualize the model fits, which in my experience, not many stats packages allow you to actually visualize how well your model fits your data. I don't know how important this is, but it produces graphs in PDF format. I guess everybody else does that now. But that means you can import them into graphics packages like Inkscape, also free, and edit them. you want to polish them up a little bit for your publications. It supposedly increases the reproducibility of analyses. And reproducibility is a term that is sort of, seems to me, still being defined. Different papers might define it slightly differently, but the idea is that if you or someone else does the analysis again, you actually get the same result. And you'd think, well, why wouldn't you? It's a computer, you're giving it the same result. But the trouble with menu-based statistical analysis packages is that there's no record of all of the choices that you made while you were carrying out this menu-based analysis. And so it is my experience that 10 years later, when I try to analyze the same data set, I have to do a whole pile of analyses to figure out which one I actually published. Well, the great thing about R is that it runs using scripts rather than menus. And scripts, you have to write them down, and you have to keep them in files, and that gives you the opportunity to annotate and state the reasons for your decisions, and everything's recorded, so you can go back. Another great thing about R is that it can be relatively easy to do things that are difficult or even impossible in other stats packages. You can write your own functions, not that hard. It's also a great programming tool, and we'll do a little bit of simulation just so that you can experience the fun. Also, there's just a whole world of people who are now using R. And if you have a problem, somebody's already solved it. Just type the question into Google, and you'll probably find the solution. I do this all the time. Google taught me R. Bad things about R. Things you might not like about R. One is, I told you that one of the benefits of R is that it uses scripts. Well, one of the downsides about R is that it uses scripts. It's so much easier to do menu stuff, but so much harder to duplicate. And honestly, sometimes it drives me crazy because certain things that ought to be easy are difficult. And I don't know why, but well, this course will help you get over the most basic hurdles. It's a crappy spreadsheet program, and so put your data into a program that's actually a spreadsheet program. There are free ones. And then read them into R. It takes a while to get the hang of the different kinds of data objects that R creates. We'll use vectors and data frames mostly. That's what you'll create. But when R carries out an operation on your vector or your data frame, it will create some other kind of object, and it might take you a while to figure out exactly how to extract the bits of information you want from a list or a matrix. But we can help with that too. The annoying thing about R is that so many people have created it that there's no single common syntax across all packages. So plot is old and core, and ggplot is newer, and the syntax is almost no overlap between the syntax, and that can be annoying because it means you have to keep going back to R tips for a reminder of exactly how you phrase this command, but that's why it's there. Quality control concerns. In the early days of R, people were concerned about this. You know, you do your analysis, you'd see your results, and then someone would say, "How much did you pay for that?" Well, actually, I got it free off the internet. Okay, well, how can I trust your answer then? Well, maybe once upon a time in the early days that was an issue, but there's so many people using R now that anything, certainly all the core packages are well tested. But if somebody down the hall makes a brand new package and it's available in R, don't assume that the answer is right. My tendency is to try and run the same analysis in two different packages that are designed for the same purpose. See if I get the same result and whether it matches intuition. A couple of other things I want to do in this hour. One is I want to talk a little bit about data recommendations. I'm not going to have a lab on it. We'll be manipulating data, but this is your first week of grad school. Soon you will be collecting data, your own data. Here's a few tips that will help you, and also will help you use R to analyze the data. This list that I'm giving you is modified from an essay published by Borer et al. In Bulletin of the Ecological Society of America. So basically, general ideas, general tips for grad students managing data. So their first recommendation, and mine too, is to use a scripted program for analysis. Don't use anything that has menus because it's really hard to go back and repeat your analysis 10 years from now, or even tomorrow. Menu-based programs leave no record of the analyses you carry out. You will forget. I know you will. So script files, they become your record of analyses that you did. Also, and something that I'm going to insist on in your assignments is that I'm going to ask you to submit your R code at the end of the assignment, and I'm going to insist that you surround your, that you fill your script with annotations, comments on why you're doing this, what exactly this next command is doing, or that particular option, what's key about it. So use these script files in your years as a graduate student, not just to record the commands that you used, but the decision that you made leading up to that point, because you will also forget that. As I mentioned, our Markdown is a relatively good way of taking script and making it human readable, because it will also preserve the output. So you'll see in an output PDF file or HTML file, not just the code that you use, but actually what the output looks like. It'll be right there. Another suggestion is to use something called version control. So version control means that every time you edit a file, the previous version is saved. So that if you decide 3 months from now, oh my God, I've messed up this code so much, I've got to go back to the point where I remember it working and giving me the answer that made sense, and then continuing. So version control allows you to do that, and the GitHub site is all about version control, so you can keep your files on GitHub, and there are desktop tools for Mac and PC that allow you to interact with GitHub, and it keeps all the versions of your files. Second tip, store your data in a non-proprietary format. So when you enter your data and save your data, save it as a comma or tab limited text file. Maybe Microsoft Excel will be here still in 100 years, but I guarantee you that your text files will. Because they will. They'll always be read by any package, but Excel, whether you can read Excel files, will come and go. So in my time that I've been using R, there were packages to read Excel files on pages, and then it disappeared for a year or two. And I had to figure out some other way to read Excel files. But the easiest way is to save them as text files. And then use just a spreadsheet program, whatever your favorite, to actually enter the data. Store your data in non-proprietary hardware formats. Keep your data on the internet. It's not going to die, ever. And just in case it does, I keep backup copies at home. So here's something maybe a little less intuitive, but once you've entered your data, it might have mistakes in it. Keep it that way. Because you might make a change. Oh, this was supposed to be centimeters or something like that. Tomorrow you realize, oh, damn, no, there was a different reason why that was an outlier. It wasn't just a conversion problem. But now you forget which element it was that you changed. So the recommendation instead is, warts and all, keep your text file, and then create a script that makes all the corrections for you. Then you have a record of them, and you can go back and undo them. Or you can remember them when comes time to writing the methods section of your publication. Okay, so corrections to the file go unrecorded, but script, you've got it there. Finally, I'm not going to go into detail about this, use your imagination, but use relatively descriptive names for your files. Data.txt, guarantee you that next year you won't know which data. In your text files, always include a header line. That's pretty obvious if you're familiar with using Excel spreadsheets and so on. But use variable names that are reasonably informative too. This is a data set I'm going to show you in a couple of slides, but Ray Huey and Art Dunham went to a population of lizards in Texas, I think, and they measured how fast they could run. They put them in a runway. They tickle their tails, they zoom down, there are lights, or there are recorders down the side that will record how fast this lizard runs. They'll repeat it, take the fastest measurement of the first 5. And they did this in 2 years just to ask themselves how repeatable is the measurement speed, running speed, from 1 year to the next. So a data set that contains all of their measurements is something like this. Lizard, 1, 2, 3, 4. Anyway, these are the headers. Sprint speed, 1984, and so on. Maybe this isn't the perfect header because it doesn't say what the units are. But maybe your script file will have that information. I use plain ASCII all the time, don't use symbols. When you add data to a database, add rows, not columns. And that's related to this point here, which is that you should use long format for data rather than wide format for data, and I'll show you what that means. So here's the lizard data set again. And there's 2 ways that one could encode or record these data in a spreadsheet. Wide format is shown here, and long format is shown here. So wide format is maybe the more intuitive when you have a pair of measurements on the same individual. You have one variable, sprint speed 1984, another sprint speed 1985. That's what I mean by wide format. But in general, in R, it'll be much easier to analyze your data if you put it instead in long format. You have only one variable that records sprint speed, and the second one that records which year that was measured in. And then the column lizard will indicate the measurements that you made and allow you to match them up.
I was wondering, for the titles in the columns, because I know someone had told me that as well, to not have spaces in between. And what's the reasoning behind that? Is it just R, when you put a space in between, it just has trouble reading the name?
So R will read the name, but it will change the name. It'll put a dot in between where the space is. So if you want to control that yourself. So generally spaces is best not to. Mm-hmm. And so when you're combining words, a popular way of writing the text, you can put underscores or something like that, but I like to use this font or this style of capitalization called camel, where you just initialize with capitals the first letter of every word. It looks like a camel. Another thing that you'll run into when entering your data into R is that a column of numbers should have only a single data type. It should be character, it should be number, but it should never be both. Here's an example of both. So as soon as there's a character, a non-numeric character in a column, R will convert it immediately to a character or a factor. And it's better instead to save your question mark for another column where you indicate with some score your confidence in the measurement. Dates are really annoying, and I'm just going to suggest from now on and for the rest of your life, use the international format where you put year first. Because if you use that, it's always clear in this case that the month will come before the day. Whereas typically in Canada, we go day, month, year, whereas in the US, they go month, day, year. And if you got a file where the date is 4/4/2012, what is it? I guess it doesn't matter in that case. Okay, 4/6. 4/6. Or use different columns. But be careful when recording dates that you're absolutely consistent and it's foolproof. Create a relational database. So try not to cram all of your information into a single file with many repetitive rows. For example, you'll have one file that contains all of the physical measurements that you took of the sites that you visited as part of your field study. And another file will contain measurements of all the species that you calculated or that you collected at those sites. And as long as the variable site is present in both files, you can match them. And that's what I mean by a relational database. You don't have to put all the physical and species measurements into the same. Maintain effective metadata. So 10 years from now, you won't remember what the site looked like, which sample you left out of the analysis, how you assigned a single value for depth of a pond. How did you measure depth? Where did you measure depth? Is this an average of 5 measurements? What? So record stuff, just record stuff, every decision you make. Annotate, put it in your script file, put it somewhere. Because by the time you have to write the methods section of your thesis, you're going to forget some of these things. And data more and more are being deposited in online databases like Dryad. It's a condition of publication for many journals. And so what that means is that people will be potentially accessing your data in 100 years from now. So make it good, make it clear so that whoever reads this data and downloads it knows exactly what you meant by a particular measurement. So keep that data on hand at the time that you make the decisions of how to take the measurements. Names of all files, etc. Okay? And there are metadata standards that you can examine and perhaps employ. Okay, so those are sort of general data management. And that's about as much as I'll say about data management, but there's lots of advice out there on how to do it. And this certainly will help you analyze the data in R. Where does data come from? Well, you'll be collecting your data, but you can also steal it. Like the lizard data, I took it from a scatter plot in the original publication. And you may not know this, but there's absolutely no copyright on data. Graphs you cannot duplicate in another. You can't duplicate somebody else's graph in your publication because that's a work of art, and that's copyrighted in some way by the individual who drew it or the journal that published it. But the data themselves have no copyright whatsoever. There are colorful tools like Data Thief, which will allow you to digitize data points on plots. That's how I got the lizard data. So that's okay, you're allowed to go get data from wherever. You won't be committing a crime. Now, more than ever, papers require that you deposit the data online at specific archives. So most of the ecology and evolution journals require that you publish your data, that you deposit your data at Dryad. Sometimes there will be conditions listed. If you use this data, please respect the author's wishes, that, So respect those wishes, that you'll find them there. So that by depositing your data, you actually are able to state what conditions you think should be met if someone else publishes your data. Okay, so this is the second course. And it's been at least 4 months since you finished your first course in data analysis. And so you've forgotten some things. So what I thought I would do in the rest of the talk is go over a few simple principles. And these represent what I think of as like the core ideas in data analysis. And we'll be bandying them about in discussion. And I want to make sure everybody knows, therefore, what those terms mean when we use them. So what's probability? Does everyone have a pretty understandable definition of? Anyone want to give it a try? What's the definition of probability? You probably maybe even published that word before. What did you mean? Everyone's looking down, just as I thought. The chance difference between an estimate from a random sample, like sample mean, x bar, and the population parameter being estimated, the population mean, mu, the chance difference between your estimate and the thing you're estimating is called what? One of the most important concepts you'll ever learn in data analysis is this one. So I really want to make sure that you know what that is. I'll go over it on the next slide. But if anyone wants to yell it out, go for it.
The variance?
What's that?
Is it the variance?
It's not the variance, but idea is there. A systematic discrepancy between estimates of a parameter and the true value of the population parameter is called?
Standard difference. Standard difference.
Not exactly. A systematic discrepancy.
Standard difference.
Bias?
Bias. That's exactly right. The probability distribution of values of an estimate that we might obtain when we take a random sample from a population and the probability of their occurrence is called the... So the idea is there's a population out there, we take a random sample, we calculate our sample mean, x bar, but what we know is that if we went back and took another random sample, we'd actually get a different value. So there's a probability distribution of values we might get for x bar. What's that probability distribution called?
Sampling distribution.
Sampling distribution, that's right. The standard deviation of that sampling distribution is called the
Standard error.
standard error, yeah. Oh, good, you guys are on a roll. A range of values surrounding the sample estimate that's likely to contain the true value of the population parameter is called the confidence interval. Finally, the probability of obtaining a discrepancy from the null hypothesis as extreme as that observed, if the null hypothesis were true, is called the p-value. Okay, here's that. What's the definition of probability? So it turns out that there's more than one. But for the most part, we'll be using this one here. And it's known as the frequentist definition. Probability is a long-run frequency. Because the proportion of times the event would occur if we repeated a random trial, like a coin toss or take a random sample, over and over again under exactly the same conditions. So that's the definition of probability that we'll use. It's a frequency. The chance difference between an estimate based on a random sample and the thing you're trying to estimate, the population parameter, is called sampling error. So that's different from bias, which is a systematic discrepancy. The chance difference is just the noise. That's variance. And you guys did well on these. The distribution we might obtain is the sampling distribution. The standard error is the width, the standard deviation of that distribution. Confidence interval is an interval that's likely to contain the true value, and the p-value is this mouthful. So I've written all these and added them to or will add them to the PDF that's online. So I'll put that on later. I pulled them for just the purposes of before the lecture, but you'll have a written record of it. Okay, a few true or false questions for you. If a 95% confidence interval for the mean is calculated from a random sample, 0.9 to 0.3.1 is the confidence interval that we calculate from that random sample, then we can say that there's a 95% chance that the mean, mu, lies between 0.9 and 3.1. True or false? How many say true? How many say false? How many are sitting on the fence? You're graduate students, you're out there. Okay. The probability that an individual is blinking when a photograph is taken is about 0.04. My experience is higher than that. This means that if a photo of two people is taken, the probability that at least one is blinking is the sum of those two. 0.08. How many say true? How many say false? Oh, thank you. The p-value from a test of treatment effects in a clinical trial was calculated as p equals 0.12. The null hypothesis of no treatment effect is not rejected, because P is greater than 0.05. We can conclude that the treatment is not effective. How many say true? How many say false? The p-value from a test of treatment effects in a clinical trial was calculated as 0.12. The null hypothesis of no treatment effect was not rejected, as above. We can conclude that the treatment effect, the difference between the treatment means, is small. How many say true? How many say false? I'm not seeing everyone's hand. The p-value from a test of treatment effects in a clinical trial was calculated as 0.001. The null hypothesis of no treatment effect was soundly rejected. We can conclude that the treatment effect, the difference between treatment means, is large. How many say true? How many say false? No. They're all false. Every single one of them is false. And if you're not sure why they're false, come to my office hours, or brush up on your introductory statistics book, because those are pretty key concepts. This is the one that most people get wrong. The reason you can't say that there's a 95% chance that the mean lies between 0.9 and 3.1 is because probability is about something random occurring, the outcome of a random trial. But this is a constant, that's a constant, that's a constant. There's nothing random about it. Either the mean is between those two numbers or it's not. What's random when you calculate a confidence interval? The random trial part is the taking of a random sample.
Does that mean that 95 or 100 times it would be like, it would fall in that bracket?
Nope.
No, it doesn't mean that.
Nope.
Okay.
It means that 95% of random samples that you take and use to calculate a confidence interval, 95% confidence, will contain the true mean.
Okay.
You won't know which one did and which one didn't. You just know that the process itself has a 95% chance of capturing the true mean, but it doesn't mean that it lies between any two values with specific probability. This is a concept. This is a constant according to the definition of probabilities that I gave. You all know this. They're not mutually exclusive events. You can't add the probabilities. And you got this right. So, not rejecting a null hypothesis is completely uninformative. You don't know whether there's a treatment effect or not. And it's for this reason that I say now and I will say again that no important decision in biology should ever be based on a p-value alone. Just because the null hypothesis is not rejected doesn't mean that the treatment effect is small. You have no idea what the power of your test is. Just because you soundly reject the null hypothesis doesn't mean the effect is large. It just means maybe you had a pretty good sample size. Okay, so again, P is not actually that informative. It usually does not tell you what you need to know. It's often treated by the scientific community as a ticket to publication. But beyond that, really, it has no use. I mean, we'll still calculate them, but that seems to be how they're treated. So here's sort of a list of concepts that maybe you should review. And if you got any of the answers wrong, to the list of questions that I gave. Because yeah, we'll be tossing these terms around, and I want to make sure everybody understands what they mean, so that there's no misinterpretation. Okay, here's a couple of others that I just want to mention before finishing. The p-value from a test of treatment effects in a published clinical trial was calculated as 0.001. This means that if we repeated the experiment, it would likely again reject the null hypothesis of no treatment effect. See what I mean? Somebody did a study, P was highly significant, 0.001, it was published. if you repeated the experiment, you can assume that you would probably also reject the null hypothesis. How many say true?
Ideal situation?
How many say false? Actually, I don't know the answer. Let's find out. Here's another one. The effect size from a test of treatment effects, like the magnitude of the difference between the groups, effect size from a test of treatment effects in a published clinical trial is estimated to be large. This means that if you repeated the experiment, it would likely again estimate a large effect size. True or false? So repeat the experiment under exactly the same conditions, but you're now going back to the population that they went to and they carried out their study, and you would find a large effect size again. So these two questions concern what is discussed a lot in the literature these days concerning the reproducibility of published results. And there's different definitions. I like Goodman's, where they sort of have two kinds of reproducibility. Results reproducibility is basically, you would get the same results if you carried out an independent study with procedures as closely matched to the original study as possible. Same results. Inferential reproducibility, you would draw the same conclusions. Those aren't exactly the same thing, although they seem kind of close. Reproducibility often means if I went and uploaded the data from Dryad and analyzed the data again, I would actually get the same results. You'd be surprised how often that turns out not to be the case. So simply analyzing the same data supposedly again does not always produce the same answer. But reproducibility also seems to capture the case where you now repeat the study. You don't just reanalyze the data, but you repeat the study and then see if you get the same result. So you're all, new graduate students, you're idealistic, you want to produce something new and innovative, and who wants to repeat a study that's already been done? Like, what career path is bad? Well, it's not bad if you maybe scale up your ambition again a bit. Repeat 100 such studies, which is what this collaboration was about. So there's a paper, there's 27 authors on this paper, and they're all in psychology. The advantage of psychology is the same humans. You can actually, everyone's working on the same species, so that you can repeat the experiment again. So what they did is they repeated 100 experimental and observational studies that they found in the literature. They consulted with the original authors, they tried to reproduce the same designs, the same sample sizes, just to ask the question, what do we get? Here's what they got. Here's the original study p-value. Here's the replicated study p-value. There is a correlation between those two. It's like 0.3. So the median p-value of the replication effects was 0.2. About 30 times that of the p-value in the published literature. Like I said, a low p-value is often treated as a ticket to publication, and so it won't surprise you to learn that 95% of the original studies have statistically significant results. What happened to the 3%? They may have made some analysis mistakes. I haven't dug in further. So 97% of the original were statistically significant. They were virtually all at or below this number. But only 36% of their replications were statistically significant. So note the different scales here. So here's a study that had a p-value of 0.01. The next time it was repeated, it had a p-value of 0.96 or something. So this is to help you answer those two questions that I asked for. What is going on? This is psychology. You could think, oh, well, it's not biology. Phew. No reason to think this would be any different. Effect size. So here's the original study effect size, which they summarized in terms of a correlation coefficient. And here's the effect size of the replication. The correlation between the effect size is actually higher than between the p-values. So here the correlation is 0.51. So not bad. But the median effect size of the replicated studies was about 1/3 that of the effect size of the published study. So even effect sizes are affected. What is going on? What do you think you don't get the same result on average or on median? Why would you not, at least on average, get the same result the next time you carry out a study?
Were they doing all the experiments with like all new people, or were they just
Yeah, another random sample of
Yeah.
a design as close to the original as possible. Any thoughts? Any ideas as to why you would see systematic differences like this?
I think there's a skew on what gets pushed to publication as being, really significant or really big effects, and some of those are going to be by random chance or by things that aren't necessarily
that's right.
a true effect.
Yeah, so a pernicious side consequence of making 0.05 your ticket to publication is that the published literature is a biased sample of all the studies that have been conducted. So when you read the literature, you can hear, it's sort of, common knowledge that don't believe everything you read. Well, believe nothing you read. At least don't read the literature thinking that you would actually get the same result if you repeated the experiment. That only the lucky ones get published. And you think, well, why the effect size? Why is the effect size influence not just the p-value? Why do you estimate on average a smaller effect size? P-value you can understand. P-values bump around all over the place. If it's 0.05, you publish it. Why effect size?
Is this too many uncontrolled variables? Is too hard to exactly replicate an experiment?
I mean,
Especially if you-
that could be, that could be a criticism of the study that, no, they didn't do it exactly the same way, so why should
But
you
you
expect?
think that, well,
Do you think it would average out? I don't know.
yeah.
I mean, I think publication bias is the answer again. Like if the true effect size is like this, and you carry out your study and your estimate of the effect size is like this, chances are P is not going to be less than 0.05, or it's much less so that if by chance you overestimate the effect size. So generally, overestimating the effect size is more likely to lead to a statistically significant result. And so those significant results that are published, if they're a biased subset, overestimate the effects that they're testing. And this has different names and different disciplines. So, published results are biased. And generally they're biased because we carry out experiments that have low power. And when experiments are carried out that have low power, those that do find a significant result are published and then they're found to be biased if repeated. So we still have to verify even what we think we know. Maybe this course will help us to understand some of the reasons for this and to make us think more carefully about our own data and analyses. So presentations start next week. Our first discussion is next week. Here's the reading, and it's available. It's up on the website for the course. The title of the paper is something like "How to Display Data Badly." How to make a bad graph. We've all done it. So 2 people are going to present on this topic next week, and then 2 are going to moderate a discussion of the topic. And those 2 pairs of people should be talking to each other as well. If anyone is interested in doing this, if anyone would like to volunteer, who's registered in the course, come and see me right after the lecture, and I'll sign you up. If I don't have enough volunteers, then I'll use a random sampling procedure in R to select a name, and I will be in touch. Sound good? So I will see you Thursday here for the first our workshop. So it's just an introduction. If you're already familiar with R, it might be a little boring, although I stuck something at the end that will at least tease your brain a little bit. Okay, any questions?
Wait, I have one. Do you recommend doing looking at the workshops before coming as well, or just coming?
Do I recommend looking at the
work
workshops beforehand?
and then
How can
coming
you
with
resist?
questions? Yeah. Okay.
I think if you have some idea of what we'll be doing and you want to maybe prepare and at least scan our tips to get an idea of what sorts of commands will look like that do those things, by all means. Okay, thanks everyone. See you Thursday.
Thank you.
There.